Hello student to the foundation of classical electrodynamics course. So, today we will have lecture number 13 under the module 1 mathematical preliminaries, and today we will going to learn the curvilinear coordinate system. Class number 13, and today the topic is curvilinear coordinate system. Curvilinear coordinate system. Okay, so this is a general kind of coordinate system today which I want to discuss, and please be careful because there are lengthy calculations and conceptually this is very enriched. So, I want want you to concentrate more on this today's class. So, the general notation for this coordinate system is this. Let us first define the general notation. So, I am not using Cartesian coordinate system, I am not using cylindrical coordinate system, or I am not using the spherical polar coordinate system. So, this is a in general coordinate system, and the general coordinate system demands some general notation, and that general notation now I am. So, the three coordinates we write with this u1, u2, u3 like x, y, z. So, in Cartesian coordinate system u1, u2, u3, in Cartesian coordinate system it is simply x, y, x, y, z. In cylindrical coordinate system it is rho, phi, z, and in spherical polar coordinate system it is r, theta, phi. So, in general now I am writing it is u1, u2, u3. Okay. This is what? This is the three coordinates, denotes three coordinate. Okay. Since we are denoting the three coordinate system, three coordinate the notations. So, now the next thing I will like to note, I like to mention is the unit vectors along these three coordinates, along these three coordinate point, and these three unit vectors are E1, E2 and E3. This is the generalized way to write the unit vector. So, these are the corresponding unit vectors. Okay. So, similarly, I can write here that E1 E1, E2, E3 for our known three coordinate system, this is simply I, j, k for Cartesian coordinate system, then rho unit vector, phi unit vector, z unit vector in cylindrical coordinate system, and finally r unit vector, theta unit vector and phi unit vector in spherical coordinate system. So, this is the way I am writing here. So, E1, E2, E3 and U1, U2, E3 the coordinates and the unit vectors, and this is a general notation. Now, for this general coordinate system, now the fact is, if I want to find out the infinitesimal displacement, how to write it. So, the length distance element displacement So, this infinitesimal displacement in general one should write like ds, let us put a vector here, is h1 d u1 and then u1 unit vector plus h2 d u2 e2 unit vector and h3 d u3 e3 unit vector. Okay. So, now this h1, h2, h3 are important here. Let me first define, then I will discuss it. This hi in general, I goes to 1 to 3 is simply the scale factor. It is called the scale factor, and for different coordinate system this scale factor differs. How it differs and how to calculate, we will discuss. This is a scale factor that relates distance dsi to change of coordinate. You may remember that for Cartesian coordinate system, the distance, if this is a Cartesian coordinate system, say x, y and z, the distance ds, this is the vector we use. Right. But if I want to find out the distance in cylindrical coordinate system, it is not that simple. That is why the scale factor is here. So, if I compare this general distance, the way we define the distance vector here and the distance vector that we have, the simplest case for Cartesian coordinate system, then if I compare, say this is my equation 1 and this is my equation 2, equation 1 is a generalized version of equation 2, then I can readily find one very important thing, and that is the scale factor h1, h2 and h3 is 1 for Cartesian coordinate system. If you simply put h1, h2, h3 1, then from this equation 1 you will get equation 2, because in equation 1 you have dui. What is ui? Ui is the coordinate. So, here we also have the coordinate x, y and z. So, here you have dui, du2, du1, du2 and du3, and also you have a unit vector e1, e2, e3, and this unit vector is representing here in terms of I, j, k, because we are dealing with Cartesian coordinate system. So, that is the information we have the first hand. Now, another thing, that how to calculate the this h, and that is a very important thing. Now, I am going to say that d square. So, I am giving you a recipe here. D square, this is the square of a distance, is simply dx square in Cartesian coordinate. It is dx square plus dy square plus dz square. Okay. Now, these things is in Cartesian coordinate system. In general, what is this value? This is h1 square d u1 square plus h2 square du2 square plus h3 square du3 and square of that, because ds is defined in this way, and if you make a square of that, then I will get this result under the condition that E I j is delta I j. So, that means I am still in orthonormal coordinate, even though this is a generalized coordinate, but this coordinate is orthonormal in nature. So, I am having this in my hand. Okay, that is why I can write it. So, from that I like to note here, make you note h1 square, I can have simply this, or h I rather, I can simply have this, you just correlate this delta x delta ui, if I want to find out I, square of that, plus delta y delta ui, square of that, plus delta z delta ui, square of that whole to the power half. So, this is a very important expression. For the time being, let us consider this is true, and then we will show in the later case that how it is coming. But intuitively you can write it, the h factor, in terms of x and u in this form, where x, y, z in the Cartesian coordinate system and u1, u2, ui are in different coordinate system, the coordinate system if I want. So, if I know the relationship, if you know x as a function of u1, u2, u3, y as a function of u1, u2, u3, and z as a function of u1, u2, u3, then eventually you can find out the scale factor. So, from here, from this information, we can find out the scale factor. Okay. So, that is the information we will going to use later. Okay. Now, let us try to understand this curvilinear coordinate system. As I mentioned, this is not any, this is a so I can have simply a volume element here, and that volume element is not a regular volume element. So, it can be something like this. So, let me draw it. So, maybe I can have a arbitrary volume element, it looks like this. Okay. And here I am having, say, my coordinates. So, these are the coordinates and this is the volume element, a very ugly looking volume element, but this is the generalized version. I do not have any spatial geometry here, just the arbitrary thing, and try to correlate with the. So, what is E1 then? What is E1? From here to here, the unit vector. Okay, I need to do it in a different color. So, this is the color. So, along this direction, this is, say, okay, let us make so this, and along this direction we have unit vector, and along this direction we have unit vector. Suppose this is my E1, this is, say, E2, and this is, say, E3. So, this is the unit vector that is distributed along these coordinates, and this is my U1, the coordinate wise, this is U1 and this is U2 and this is U3. Okay. So, what are the surface element that it is better that we can find? What is the surface element here? So, this is so along this direction we have I. So, okay, the distance, first we try to find out the distance from here to here, from here to here, from here to here, because the scaling factor is there. So, the distance if I calculate, so from here to here the distance is this d S1, this is the distance, and this distance is scaling factor multiplied by du1, right. Every time you need to multiply the scaling factor when you calculate the distance. This one is d S2, which is scaling factor to du2. I am talking about this distance, I am talking about here this distance, and finally here, or this one maybe, it is d S3 is equal to scaling factor H3 and then d U3. Along this direction it is U3. Okay. Now, with this coordinate system, if I define the gradient of over a function, how it look like, that is the first thing we will do today. So, I will try to find out the gradient. Operation, and we know the gradient operator, how it operates, but for curvilinear coordinate system, what is the form that we want to check. So, let us start with this scalar function. Let us start with this scalar function. If u1, u2, u3. So, this is my scalar function or scalar field. Now, what is df here? We know it. This one, right? And also we know that df is equivalent to the gradient of f dot the distance vector. Okay, that we know. This is the identity. This is the fundamental identity we have. So, keeping that in mind, I can have this. If I expand, what I get? I get, okay, I have the gradient and the dot product. So, in Einstein notation it is I and dSi, right. What is dSi? It should be Hi and then dui. Okay. So, df, if I find whatever is written here, df is ith component and ds I write it as my Hi dui. Okay. So, what is the ith component? What is this then? If I write this, okay, the gradient of the ith component is simply 1 divided by Hi del f del ui. So, this is the general way to define the gradient, in curvilinear coordinate system. This is the way one can define. Now, you can appreciate that, you should appreciate that this H1, if so for Cartesian coordinate system, what happened? So, if I want to find out this quantity in x, y, z, this system, then for x it is simply del f del x, right. I am just writing the component, not the vectors here, and whatever here y, if it is y, then it should be y. So, let us put, otherwise it will be confusing. So, I am just taking the x component, but it is the Cartesian coordinate system. This is the Cartesian coordinate system. Now, similarly, if I want to find out these in other coordinate system, if I want to find it in other coordinate system, like what is this in rho phi z. So, I need to find out. So, the general form is I need to find out the h factor of rho and then the function derived by rho. Okay. In the similar way, if I want to find out in polar coordinate in spherical coordinate, then I need to find out the scaling factor here, and the scaling factor is r HR, and it should be del f del r. So, this is the way we should proceed, but you should remember that the general form is this one, the general form is this one. Now, next after that I like to extend this idea for divergence, how to calculate the divergence. It is a little bit lengthy calculation, but straightforward. So, let me check how much time I am having. Okay. So, let me quickly show, before that let me quickly, because we are here, quickly show how to convert, how to find this H rho we are talking about, right, and we already had this information in our hand. So, how H factor one can calculate. So, I mentioned that if we know the relationship with x, y and z with u1, u2, u3, then you can calculate, from this you can calculate h1, h2, h3 for different coordinate system. So, for let us do that for cylindrical coordinate system. So, that let us do this exercise whatever the time we have. So, for cylindrical coordinate system, we have the relation, and that relation I am going to exploit. X is equal to rho cos phi, y is equal to rho sin phi, and z is equal to z. What is my aim? To find H rho, H phi and H z. These are the scaling factor of the cylindrical coordinate system. This scale factor I want to find. This is my aim. And how we find that? Because I know the general, I know how to find Hi in general. Hi is this one, del x del uy square plus del y del ui square plus del z del uy square whole to the power half. This is the recipe. This is the recipe I am having. Okay. So, this recipe I am going to exploit here. So, what is now the first thing I calculate is H rho. So, H rho will be how much? Okay, let us calculate. So, the first thing is this. So, it will be del x del rho square plus del y del rho square plus del z and del rho square whole to the power half. According to recipe I should write it. Now, what is this quantity? This is known, right, because I know the explicit dependence. I know the explicit dependence. So, if I make a derivative, so x is rho cos phi. So, if I make a derivative with respect to partial derivative, so this value is cos a square phi. Then I have sin square phi, because I know the relationship with y and rho, x and rho phi, y with rho phi and z, and finally z. But you can see that there is no dependency over rho in this. So, I can have this plus 0 whole to the power half. Now, this quantity is simply 1. So, the first thing I find here is h of rho is equal to 1, that is the first thing I find. Okay. Next, I need to calculate what is h phi. H phi is simply del x del phi square of that plus del y del phi square of that plus del z. You just go with the recipe that is shown there, then whole to the power half. By doing this, what we have, let us check. So, I will need to make a phi derivative with respect to phi derivative here. So, x is there. So, I am getting the value this. So, it should be rho square, and when you make a derivative with respect to partial derivative to phi, cos becomes sine. So, it should be sine square with a negative sign, but square is there. So, I will get simply sine square phi. This value will be rho square cos square phi, and again the last value is 0. So, to the power half. So, we are having now an interesting value here, and that is h phi is equal to rho. So, the next thing I am getting that h phi is equal to rho. The scaling factor is no longer become 1 here. Previously, for h x, h y, h z or h 1 2 was 1 for Cartesian coordinate system, but here this is not the case. And finally, what is h z? Very straightforward, because z is equal to z. So, I mean, even if you do rigorously, you will get 1, but from just looking the expression you can get the value 1 square square sorry, this is z square whole to the power half. So, this value is 0, this value is 0, and this value is 1 whole to the power half. So, you will get simply 1. So, for cylindrical coordinate system, I will evaluate we have what we have this h rho is equal to 1, these are the scaling factor, h phi is equal to rho, and h z is equal to 1. So, this is the scaling factor we are having for cylindrical coordinate system. Okay, I do not have much time to elaborate that. So, in the next class maybe we can find out the scaling factor for the spherical polar coordinate system. The process will be exactly identical, and if you find some values, we will find some values, and exploiting that values. Now, the next thing is to how to understand what should be the form of this operator, the divergence operator, and then the curl operator and the Laplacian. How this operator, Laplacian operator, divergence operator or curl operator will look like in different coordinate system from this general expression that we are going to exploit. So, already I figure out the HIs for in cylindrical coordinates in Cartesian in cylindrical coordinate system. So, you know that if I want to find out here, so these values if I going to use, so what value we will get? This I now calculate in cylindrical coordinate system, rho phi z. The scaling factor is now known. So, in the first value it should be simply del f del rho. What is the second value? Because h rho is 1. What is the second value? Second value with the unit vector rho unit vector. And then what is the second value? Second value is 1 divided by rho, then phi unit vector del f del phi. This 1 by rho term is coming because of the fact that h rho h phi is equal to rho, that we just calculate. And finally, again the last term, which is 1, again each factor 1. So, I have del f del z with unit vector z. So, this is the form of the gradient operator in cylindrical coordinate system. You can do that also for spherical coordinate system, and you will see that the form is different, but in that case we need to find out the h1, h2, h3, the scaling factor for this spherical polar coordinate system, that we do in the next class. So, I do not have much time today. So, with that note I would like to conclude. So, thank you very much for your attention. So, see you in the next class, where we are going to expand more about this curvilinear coordinate system and trying to find out the scaling factor, and eventually we will get the expressions of the curl operator and then divergence operator and the Laplacian operator. Thank you very much. See you in the next class.